Let's continue the discussion on pointers. And the last Friday conclusion was that in order to make a program in which a function can access other functions variables, the only solution is given by pointers. Because we have seen last week that pointers are numeric variables which are used to store numbers, which numbers always represent an address. Okay, so for other variables like an integer, a number could be, I don't know, number of students, number of classes, whatever. But for a pointer, it's always an address. Okay, so yeah, let's define main in order to test something. We also explained with return 0 why we don't write it and why here we have an integer, because by default, all these processes return that error code, and 0 means no errors. Okay, and also because we will print something, I will use the iostream library. Okay, and remember the talk we had regarding why we sometimes write using namespace standard, why this is not, let's say, recommended in real projects, and how do we cope without using namespace standard, like writing the prefix each time. Okay, so today I'll do let's say a combination of using by default the standard namespace, or by writing the prefix again. So if you don't write the using namespace standard and you want to just print a message on the screen, this will be the way. And this is the way you should code the entire program without the using namespace standard. Okay, so let's say course 3. Okay, so and this way, okay, I don't need the using namespace standard. But like I said, sometimes in order to do more in the little amount of time that we have, we will use the using namespace standard to just skip this part where we write this prefix again and again. Because if we have a lot of printings, this can take up some time to write each time the standard 2 points prefix. Okay, we know from last week that each function has its own sandbox for storing variable, and that's called the stack frame. And today we will draw it, so we will actually see it on the screen. Okay, so let's define some variables here in main. Okay, so I will define two values, value 1, value a. Let's say value a sounds more scientific. So value a equals 10, and after that I will say value b equals 20. Okay, and also let's suppose at some point we have an array somewhere here. Okay, int values. Okay, and I will go for an array with predefined values like 1 2 3 4 5 6. Okay, 6 values. I have this array, and a conclusion from that I was telling your colleagues yesterday is that every time you define an array, don't forget to define also a variable which will be used to store the size of this array. Okay, so in this case is 6. Okay, because I have 6 values here. So I have value a, a value b. I have some integer values here, number of values, again another variable. And okay, so all these variables right now are on the main function stack. And we talked about pointers. So if we do programs with only one function like main, which will not happen, so we will gradually add multiple functions in our source code starting today, then it's very improbable that you will need pointers, because even if you want to store a large amount of data, you can still define here a very large array. So you can actually avoid pointers if your program is simple. Okay, if you just develop a basic app and you write everything inside main, but things are going to change. So at this point, let's define a pointer, which may have no reason to be here because I have all my variables, A, B, values, number of values. But let's see, I want to, let's say like a short recap on what we talked Friday, to define a pointer to be able to change value of A either by the variable itself or by the its address. Okay, so again, just to warm up, let's remind how to use pointers to do that. Now, at any point you may say, hey, this doesn't make any sense because you still have the variable here. So why do you need to increase the complexity of the source code to do the same thing by just using the variable name, but with a pointer? Okay, so it's just for the sake of the example. So in order to define a pointer, I know that if a pointer A, okay, so this is pointing to A, to value A. So at this point, this is not a pointer, it's just an integer because it's the same definition. Okay, it's an integer, it's an integer. So I know that in order to make the difference, I just need to specify that this variable is kind of special because it's not just an integer, it's a pointer to an integer. Remember, if we want to define a generic pointer, and malloc, which you used for so many times when you created space in heap, was actually returning a pointer, a generic pointer, looks like this. Okay, and we talked about it last week. So this is a generic pointer, which means this is just a pointer to anything. Okay, so the difference between this and this one, it's a logic one. Okay, because if you just ignore this part, so if I just delete this and this, both are the same. Both are pointers, which means the same type. Both these two variables have the same scope to store addresses. Okay, now how this makes the difference? So like I said, it's a logic difference because here this will always refer to what's there in memory at this address. Okay, and here it's obviously that at any address that this variable will have, pointer A, we will find an integer because this is what we said. Hey, we will use this pointer to manage integer addresses. So that's why this is the reason of this type here. Okay, to say to the developer that at this address in memory, and the address will be given by this variable, will be an integer. Okay, so we know that this pointer will point only to integers in memory. This one is a pointer to anything we want. Okay, and in order to use it to actually read something from there, remember the cast operator. Okay, so right now I want to print the value of A. Okay, so I will do cout end line. That's also the Visual Studio IntelliSense, but I don't know what I did to deactivate that one. Okay, so yeah, in other projects I see that, so it's here. Okay, yes, something like this. Yeah, yes. Okay, but I don't know why for me that's not showing up. I'm sure there is a option somewhere, but don't know how to reactivate it or so. So in your case, the warnings are also showing up here. And if you hover the mouse over them, you'll see this message. And also, if you click on that tooltip, sometimes it can suggest you to fix it. Okay, to provide an initializer, for example, it will say, hey, make it null. Okay, so yes. Yeah, so if you have that, it's okay. So, but like I said, I don't know how to reactivate that for me. Yeah, you'll see the warnings on those specific lines. You see, I have them here if I need to check them, or yeah, because I selected the warning here. Remember, sometimes Visual Studio will recompile your source code, but many times it will not. So always build, rebuild. Okay, this should be like I don't know, a good habit. Okay, from time to time, just go build, rebuild, because otherwise it would be trickier. you will say, hey, I have no errors, but you actually have, and Visual Studio stopped compiling your source code after you type. So always do force the compiler. So here I initialize pointer a just to remove one of the warnings, and I can do the same here with null pointer again. So let's print the value. A value is, okay, and here I want to see the value A, okay. And if I want to do the same, this is what we try to do the same with the pointer, I will do this. Pointer A equals the address of value A. Remember, if you try to do this, the compiler will say, yeah, but this is an integer and this is a pointer to an integer. And the power of cast is that we can override all these issues with equals. So we can say to the compiler, hey, I don't care. I know what I'm doing. So just let me. So here, if you do this cast here, right now, you see the compiler says, okay, they have the same time, the same type. I will do what you want. But the issue here, this is a mistake. Why is a mistake? Because now, what's the value of pointer A? So the pointer value is going to be
A in hexa, like
A in hexa, like A the variable.
yes.
So what's the value of value A in decimal?
No, 10.
10. So pointer A will take the value 10. And if we print this on the screen, it will be 10 in hexadecimal, which is A.
A, yeah.
Exactly.
Well,
so
it basically takes the address of, like, it makes the value an address and it looks at the address. And it shouldn't
exactly.
that.
So right now we use the value A value as an address, which is wrong because, like I said, in RAM, the address 10, it's at the beginning, and most of the times those there is the reserved space for, I don't know, kernel, Windows, and we are not allowed to go there. So if I will print the pointer, just to prove what your colleagues just said, so cout, I will say here the value of the pointer, and always a value of the pointer is the address. Okay, it's an address. That number, it's an address. The value of the pointer is, and we just print it like a normal variable. Okay, so build, rebuild, start without debugging. Okay, let me show you the screen. Here it is. You're right. The value, A value is 10. I will put an end line here. The value of the pointer is A. Okay, and now if you try to read, to use the pointer to read from memory at this address A, the program will crash because we are not allowed to go there. So the address exists, but like I said, it's protected by the operating system. Okay, the address 10, I'm sure for about that. So we can try just to show you that it will crash. So the value, and here will be the value at the pointer address. You see the difference? Because now I want to see what's in memory at that address. And obviously, using just the pointer name, it will just print it like a normal variable. So in order to see what's there in memory, we use, again, the asterisk. So right now, if I'm trying to do this, it will crash. Start without debugging. Windows Defender is saying that something is strange. I will try it again. And here it is. Okay, exited with code. Okay, and you see, I don't see the output. So it just stopped on the previous output, and after that exited with a strange code. Okay, and this is what we did last week. So generally, we don't set values to pointers directly, because if we don't know what we do or what's the final goal for that, maybe we want to hack the system, generally it will the program will crash. Okay, end line. Okay, so let's do another end line. Okay, this will not work, okay? Because the mistake is here. The pointer value is going to be 10. Okay. So generally, when we have a pointer, we don't do this. We don't take values from other variables. We take addresses, okay? So the correct way to initialize a pointer in 99% of the cases, the other 1%, if you want to hack the system, okay? But for normal users, this is actually like this. So you see, you write value A. Now, again, the compiler will say, hey, yeah, but that's an integer. And here you have an address of an integer. So I will say, okay, sorry, I don't want the value of the integer. I want its address. Okay. So generally, this is the way we will initialize pointers. We will initialize them with addresses of our own variables. Because in that way, here we will always get a valid address. Okay, so here we will get an address from our own space, which we are allowed to read and write later. So in 99% of the cases, this is the way we will initialize the pointer. So if I run now the same program, build, rebuild, debug, start without debugging, again, Windows Defender is playing tricks. Sometimes I need to rerun the program 2 times. Okay, so, and if I share with you the screen, here it is. The value address of the pointer is, you see, it's not A anymore. And this is, you may say it's random. It's not random. It depends on where I get space when I run this program. And if you run this example on your machines, you will never get the same addresses as me or as your colleagues. So when you print addresses, those values will change anytime you run the program, okay? Because this is normal. Your program will be loaded into memory at different addresses each time. Again, this is just for the sake of the example to show you the value of a pointer, but generally we don't print them. And this is the last line. You see, the value at the pointer address is 10. And this is actually the value of A.
The value 10 is located at that hexadecimal number, right?
Exactly.
But
so if I will draw the memory, let's draw the stack of our function main. So let's draw it because we need to draw it in order to understand what will happen in the next minutes. What's a stack of a function? It's an area of memory in RAM, somewhere in RAM. So right now, in our program, there is only one function which is running, and that's main. This will be the main stack, okay? So the main stack is like a rectangle, okay? It's just an area of memory, and it's called stack because it behaves like a stack. So you heard about the stack data structure. If not, you will do that next semester in much more detail. Why it's called the stack? Because the stack, this memory area behaves like a stack, which means everything that you add, it's on top of what exists. Now, in RAM, there are no 3 dimensions. So there is no left, right, up, and down. It's not a 3D-dimensional area. It's actually a 2-dimensional area. So you have only left and right. So the stack actually in a 2-dimensional space. So let's say if I draw a stack of something, it will be like a vertical memory space, right? Let's exercise a little bit. It will be like something like this. So if I put something here, the first value, X, it will be here. If I add another value, it will be on top of it. And the story goes on, okay, A and so on. So the stack is filled from bottom to the top. Now, if I want to take something out, this will go from top to bottom. So the first value that I can take from the stack is A, or this is said is in on top of the stack. And after that, if I remove it, I can reach to Z, Y, and so on. Okay, so this will be a description of a stack in a normal up-down space. In memory, there is only right and left. Okay, so the space is 2-dimensional. And here, what we see here, bottom, so this is, let's say, okay, and this is top. In memory, in RAM, this is actually right, and this is left. So if you draw the memory like a line, okay, this will be, let's say, the end of the memory, and this is the beginning. Okay. And the equivalent of bottom is here. So this is the bottom. Okay. And this is the top. Okay. So when you hear about a stack, the way the data is stored on the stack is actually from end to beginning, because it's from bottom to top. Okay. So it's in the other way that we are used to read, write, see the word from left to right. So the stack generally is filling up RAM from right to left, okay, in reverse. So if I will draw the stack of main, okay, of main, we just need to follow from top to bottom, like the compiler is doing this. We need to follow the variables. So here you will have value A, value B, the array, and number of values, okay? So let's draw them. I will draw here a line, and this will be the main stack. Okay, let's continue this a little bit. Okay, and the first, just to have enough space. So the first variable that we had was value A, right? Here it is. And this is an integer. I define it. So this is A. And I know it has 4 bytes. Remember the data types. After that, we have B. This is B, another 4 bytes integer. After that, let's go back just a little bit. You have the array. So values and number of values. Okay. And this is a 6 integer array. Okay. So let's draw it here. This is the array. Okay, so here I have 6 multiplied with 4 bytes, 24 bytes. And here they are, 1, 2, 3, 4, okay, 5, 6. Okay, so this is values. Okay, after that I have number of values, is the size of it, another integer. Okay, 4 bytes. So this is number of values, number, which is 6. And after that, we have defined here 2 pointers. Okay, so I will focus on pointer A. So a pointer, it's a variable. Okay, so a pointer, it's a variable. Yeah, let's make it with the rainbow color. Okay, so this is PA, pointer A. Now, the question is, what's the size of a pointer? How many bytes it needs in order to store an address? So in order to get the answer to this question, you need to ask the processor, what's the biggest number that it can say? So if you remember, again, last year, at some point you discussed about processor, something, also you may have seen something about assembly, you talked about processor registers and so on. Now, just a resume. In the processor, there are some variables which are called registers. And those registers are actually used by our processors to process anything. And the processor is doing everything only with those registers. So those registers are actually telling us how powerful is the processor in terms of what's the biggest value that it can say. This is like, if you remember when you were a kid, maybe the first numbers you learned was you learned to count from 1 to 10. This is easy. Okay, everybody kid will do that. Let's say we know how to count from 1 to 10. So we can actually measure the world. We can actually do a lot of stuff in real life by just using only this, let's say 11 values, 0 up to 10. The big issue is that what will happen if, I don't know, my parents would say to me, hey, go to the market and buy 15, I don't know, 15 breads or something. So I will have an issue because I don't know what's 15. I can't represent it. Okay, I don't know what's that. I don't know the value. I know values from 0 to 10, but for me, 15, it's unknown. So maybe my parents will say, oh, sorry. Okay, next year you'll know about 15. Now just go and buy 10 breads, and after that, buy another 5. And for me, it will be, yeah, I know how to do that. So I will do that in two parts. And this is the way processors are doing all the stuff. So the biggest number that a processor can represent is given by the size of the registers. And now you may heard that there are different architectures of processors, like there were initially 8-bit, 16-bit, 32-bit, and now we are all using processors on 64 bits. So it means that the register, okay, the register of a processor that you have in front of you or in your smartphone has 64 bits, which means the biggest value that that processor may say could be represented on 64 bits. And 64 bits is actually 8 bytes, okay? At this moment, our processors, in order to talk to RAM, in order to say to RAM, hey, give me that value at that address, it can use 8 bytes to say that address. So on a 64-bit processor, all the addresses can be represented on 8 bytes. So all the pointers will have 8 bytes. Okay. Now, in our world, during our semester, all the pointers will have 32 bits, which is half of what our processors can do because of this option here. You see it? This is by default. And this is to provide backwards compatibility, which means we now develop programs in C++ which can be executed on x86 processors. This is the 32-bit architecture, which means we can run these programs even if you, I don't know, take from your grandparents or something, your oldest computer, okay? That one or your first computer, which may had 32 bits as an architecture, okay? An Intel Pentium or something. So because of this option, all our programs are developed for 32-bit processors. Now, the 64-bit processor has no issue with that because it can run programs for legacy architectures, but vice versa, it will not work. So a 32-bit processor cannot run 64-bit programs, okay? Because it doesn't know how to interpret those numbers. So you see, by default, we compile programs for x86, which means 32 bits. You can compile programs for x64, which is the 64-bit architecture, which is the current architecture of processors, okay? So because of this, even if we have more powerful processors, we are actually building software for the previous version, the previous architecture. So in all our programs, all our pointers will have 4 bytes, always. If you change that option there to x64, all our pointers will have 8 bytes, okay? So the pointer size is always equal with the processor architecture. Yeah, because addresses are used by the processor. So all our pointers will have 4 bytes. Okay, so this is the stack of our very simple function at this point. What has happened here? When we just said pointer A equals address of value A, I will share the screen again. So this is in my memory right now. You see the address of A when we run this program was 0099FD0C. So the address here, okay, so let's write the address of A. When I run the program, obviously, if I run it again, it will be a different address, was 00, let's see, 99FD, 99FD, and whatever. This is not important, 0C. So when we executed that instruction, that PA pointer A equals address of A, of value A, that's why this value has been written here, 0099FA, the address, okay? And that's why now we say that this pointer is pointing here, okay? And that's why when we try to see what's in RAM at this address, asterisk pointer A, the processor went here, took the value of the pointer, which is 0099FD0C, looked into RAM, and took the value and printed to the console. And what was the value we have here? It was a 10. Okay, so here we had the 10, and this is A, and this is B. And that's why we have seen 10. Obviously, using the same approach, we can actually change the value of A by writing value A equals 30, or by saying, hey, at that address, which is pointed by pointer A, write the value 90. So what's the effect of this instruction with this asterisk here? This means go into memory at the value of this pointer, which means go into memory at 0099FD0C, because that's the value of the pointer right now here. And right here at this address, write 90. Okay. So in order to prove you that this actually works, now if we print again the value of A, now it should be 90. Okay, because here we just overwritten the value at that address. And the address managed by this pointer A right now, it's actually the address of A. So at this point, every time I will write asterisk pointer A or value A is the same. Okay, they both point to the same location in memory. So let's run this again. Build, rebuild.
So what you mean is before we can assign a value to a pointer, we must first write that said pointer has a value, no matter what that value is, and only then we can change its value.
Exactly. So every time you want to use a pointer to read or write from memory, so you see now the value of A is 90. So let's go back to code. So every time you want to use a pointer to either read, so when this is to the right side of something like output stream or equals, it means you want to read from here, from this address, and this is what it's telling me you want to read, the asterisk, because you see without the asterisk, this is just pointer A, which means 009AFD. Now you play with the pointer like with an integer, okay, when you don't use the asterisk. So generally we don't want to do that. So when you have an asterisk and a pointer, and this expression is to the right of something, it means you want to read from there. Okay, this is like, hey, don't interpret the value of pointer A as a number, interpret it as an address, and just go there and give me the value. And if the same expression is to the left of equals or another expression, it means it's a left value. It means you want to change it. So here is like, go at this address, which is given by the value of this pointer, and write there 90. So yeah, every time we are using this or this, we need to initialize the pointer. And this is the cause of the most errors that we will do, which is we forget to initialize the pointer, okay? Or we initialize it to the wrong address. So you see, if by mistake now I will say value B here, after I write this pointer A equals 90, is value A going to change? If now the pointer points to value B, to the address of B. Sorry?
And it's not going to change.
I think it remains 10.
Exactly. A is now unchanged because we are actually changing the value of B, okay? Despite the fact the pointer is called pointer A, that doesn't matter, okay? The names does not matter. So everything. So you see, this is a common mistake. We initialize the pointer with another variable, and after that we are asking why this is not changed, because the pointer is not pointing to this. Okay, this is a common mistake, and we will do this kind of stuff. So that's why we need to pay attention. Okay, so this is what we can do with pointers. We can actually look in memory. Remember, if I'm giving you an address and the address is from here, and I'm giving you that address by a pointer, you can do anything with that value here in memory. You can do anything, okay? The only thing that is stopping us if we have read or write access on that memory space. But if those addresses are here on our function stacks, we are okay. So we are in the same process space. Okay, Now, in order to prove you, and after that we take the break and we jump to functions. In order to prove you that the stack is like here, like this, let's look at this image. And I will ask you this. This is like Einstein, you know, what he said, that he can move any point in the universe, but it needs a fixed point in universe because the universe is in a continuous movement, it's expanding. So if I'm giving you a point here, if I'm giving you this point here, so if I'm giving you the address of this point here on the function stack, it means you can actually see what? The number of values here, right? If you have the address here, right at the beginning of this variable, number of values. Okay. And if you take this address and you just add 4 bytes and add 4 bytes and 4 bytes, is it true that it's possible that we will actually jump through the function stack and see all the integers till the end? If this story is if this image is true, it's like this is a continuous space of memory, all the variables are arranged like this. So if we start with this address from here and we just increase the address by 4, because that's the size of, you see I have 4 bytes here, 4 bytes here, 4 bytes here, and just print the values, it means we can actually see the entire stack of our function by starting from this point. So it makes sense. By just using a pointer, we can actually see everything what's here. It makes sense?
To me, it wouldn't
Yes.
make sense that, for example, where we have B on the right, like if we add 4 bytes, then
So
we will have like 8 bytes and A is on 4 bytes. That doesn't make sense to me.
So let's translate for your colleagues. Remember, this is the end. Okay, so this is we generally read addresses from left to right. Okay, so the addresses grow from left to right, but because this behaves like a stack, like I said, it's used from the end to the top. So the addresses are decreasing from this point towards the left side of the screen, which means if this is the address of A, the address of B will be with plus 4 bytes or minus 4 bytes?
Minus 4 bytes.
Minus 4 bytes, because like I said, just try to read it in reverse. Okay, half of the word is reading in reverse. Okay, so let's try to see their word. Okay, so if you have minus 4 bytes, it means that if I start with the address and I decrease 4 bytes, I will get here, right?
Yes.
And in the same thing, if I start from the left and I'm adding 4 bytes at a time, it means I'm moving towards A and B, starting from here, right?
Yes.
Okay, so let's prove this. Let's prove that this is true.
But
So-
this is only by the chance that they come in memory next to the other, or they always go in
Yeah,
memory
but
next
we
to
can
the other.
deactivate that. We can deactivate the cache optimization and to align them in memory. It's true what you said. So let's see. I just want to just see if we can actually do this, because generally we will not do this, but maybe this will help you to see the power of pointers. Okay, if we do this exercise and you actually see that, hey, starting with an address here, if I just increase that value by 4, it's actually going through the memory and seeing other integers. Okay, and if you see this, this is the way pointers see the word. Okay, they are just addresses, and we actually play with our variables not by their name but by their addresses. So it's a dual word. You can actually play with variables by their name, or you can actually play with the variables by their addresses. And if you manage the two, now you manage everything. Okay, so if I go back to the program, okay, here, let's print here at the end. Okay, let's print the addresses just to see the difference between them. So cout end line, let's say address of A is, how do you get an address of a variable? Ampersand or and of value A, right? This is the way of value A. Okay. And now let's print the address of B. So the address of B is value B. Okay, let's see the addresses. So we just see the addresses and that's it. Build, rebuild. Okay. Debug, start without debugging. Again, the Windows Defender is just trying to make sure. So let's see. The address of A is 5FF738. Okay, just look here, 38. And the address of B is 5FF7-2C. So you see the first 6 digits are the same. Okay. And the only digits which are different are the last 2. So this is A, 38. This is B, 2C. Now from 38 and 2C, which is the bigger one?
38.
38. So which means that in memory, the address here, so I will write only the distinct part. Okay, the address here is 38 and the address here is 2C, right? 2C was. Okay, now they are in hexa. So 38 in hexa, in decimal is 3 multiplied with 1648 plus 8. This is 56, right? 56, if I'm not mistaken. So 16 by 3, 48 plus 8, 56. Now, this is 32, and C is A0, B is 11, C is 12. So 32 plus 12, this in decimal is what? 32 plus 12 is 44. Wait a minute. 32 plus 12, 44. Yeah.
Yeah, it's 44.
Yeah, it's 44. So here, yeah, it's the lower address. So at least we know B is in front of A. Okay, so you see they are like this in memory, which is great. I was expecting the difference to be a multiple of. So 56 minus 44 is 12. Why 12? Why is aligning my variables with 12? That's not okay. Anyway, okay. So earlier, one of your colleagues said, hey, this will happen if they are in memory, write each variable beside the other one. So you see in memory, B is at this address 44, and now it needs only 4 bytes. And the difference between 56 and 44 is 12, which means that actually in reality on my machine, there is a gap here of 12 minus 4, 8 bytes, okay, between B and A, which is unused space. And this is also relates with what maybe my colleague said in the first year about cache optimization, about the fact that RAM is, the compiler is actually trying to align these variables in memory with addresses which are multiple of the cache line. So what's the cache line? Just to understand why we have this difference. So you have the microprocessor here, okay? And you know, when you buy a microprocessor, there are multiple processors with the same family, let's say i7, and the price differs based on the version of the i7, especially on how big is the cache memory. So inside the microprocessor, you have a memory which is limited. It's several megabytes, and this is called the cache memory. Now, this is very fast because it's writing on the microprocessor, okay? So generally when the microprocessor, so this is the microprocessor, okay? Every time the microprocessor is saying to RAM, hey, give me a variable like this one from here, it will not just bring only 4 bytes or 8 bytes, depending on the size of the variable. No, the cache here works in lines. So, and this depends on the processor type. For example, a line could have 16 bytes, or a line could have only 8 bytes, and so on. For my processor, I see that my cache lines, because this is what the compiler has did, on my processor, the cache line, it seems, is 12 bytes. Okay, so because with a high probability, the next instruction will ask the processor to bring also the next variable from memory, from RAM. The compilers are actually aligning variables here in RAM at addresses which are multiple or of the cache line. So when the microprocessor is saying, give me B, it will not just give only B 4 bytes, it will bring the entire line. So all 12 bytes or all 16 bytes or all 8 bytes. So in that way, maybe the next variables are sent to cache, because the next time the processor will say, hey, give me A, cache will say, hey, I already have A. It's already here. Here it is. So in this way, we can process faster stuff. This can be deactivated. Okay, so this is a cache optimization option, which is by default for many compilers, but it can be deactivated. So that's why we have this gap. And that's why your colleague said earlier, yeah, we will have a difference of 4 bytes if actually they are all together here. Great. So on my machine, I see that there is this difference of 12 bytes. So in order to prove you, if I will start with the address of B, okay, so if I start with the address of B and add 12 bytes and print what's here, I will print A. Okay, so again, this is what we can do with pointers. So let's do this. Int asterisk pointer B equals address of value B. Okay, and now I will say pointer B plus equals. So if I do plus equals 12, this is where again this type matters. And again, this is what my colleague said last year. Remember, pointers arithmetic, which means that if you add a number to a pointer, this is like not actually add that value. Pointers are markers. Yeah, please.
Yeah, I want to say that you basically add 12 times the number of bytes that type of variable is set on.
Why? Because a pointer is like a page mark, right? You are reading a book and you put a page mark on page 100. And when I'm saying, hey, just jump 12 pages, what do you do? Or jump 12. You don't jump 12 words. You just move the page mark 12 pages to the right. So this number, like your colleague said, is always in terms of actual value, absolute value, is multiplied with size of this type, which is 4. So if I want to jump from here to here in order to reach A, so right now I'm here. This is like a map. You are here. So right now we are here. We know that on my machine, the difference between this address and this address is 12 bytes. What will be the number that I need to write here in order to jump 12 bytes? What's the number that I need to write here in order to jump 12 bytes?
In order to jump 12 bytes?
And pointer,
it's 3. Yeah, 3. It's 3 because it's a pointer to int.
Exactly, because now it will jump 3 multiply with size of int. So if I'm printing now value, let's see, A value is pointer B. Okay, and let me show you that initially this was actually the B value, you see? So I initialize the pointer with the value B. I'm printing the pointer, okay, pointer B. So here I'll see the B value, which is 20. Now I jumped 12 bytes in memory because I have seen the difference on my machine. On your machines, you can have different addresses. So you need to check them here and do the difference, because depends on what your processor, maybe you have a better processor than me. Maybe your cache line is 16 or maybe more, who knows? Okay, but on my machine, this should work. Okay, so build, rebuild. Okay, debug, start without debugging. Again, I need to start it again. And here it is. B value is 20. Let me share the entire screen. You can see also the source code. You see it? So Initially, we initialized the pointer with the address of B, and we printed that. And here it is, B value is 20. After that, I jumped 12 bytes into memory, and I printed the value there. But yeah, but 12 bytes in memory, starting with the address of B, is actually where A is. So you see, A value is 90. Okay, and this worked because a pointer is just a marker here in memory. And once you know where you are, and if you can draw this image, you can go anywhere you like, to the left or to the right. You just need to know how many bytes to jump. And that's all. Okay, and this is actually the power of pointers. This is what we can achieve with pointers. We can actually go to an address, and from that, we can move to the left of it or to the right of it. Okay, so we are here. When pointer B is initialized, we are here. Okay, this is the spot. And I want to move the address. I want to move the pointer from the spot here at the beginning of A. So if this is a number, which is an address, okay, in order to move the pointer from here to here, it means that at this address here, I need to add a value which will help me jump from here to here. This is clear?
Yes, and we have to see what length we have, like you have 12 bytes.
Exactly. So what I did, I was printing the address of A. You see it here and here. I did the subtraction between them, between A and B. And on my machine, the difference is 12 bytes. So the difference between this address and this address in my memory is 12 bytes. This is clear?
Yeah, and we have to do this every time we make a problem, we solve?
No, generally we don't.
Okay.
But what's important here is to actually accept the fact that pointers are managing addresses. And if we change the value of a pointer, we can go anywhere in memory. Are you okay with this one?
Yes. Yes.
Okay. So plus equals 3 here, because the difference is 12 bytes, but plus equals 3 here is because this involves the pointer's arithmetic. And when you add a value to a pointer, this is actually this number multiplied with size of int. So we know that the size of an integer is 4. And here we are doing plus equals 3 because this is in reality is actually to this value add 3 multiplied with size of int, which is 12. Okay, so that's why here it's not 12 and it's 3. Okay, just to finish this. Okay, now when we need to do this, this is important. When we need to do this, when we play with dynamic arrays of anything, because a dynamic array is actually a sequence of values in memory, generally in heap. And the only thing you have there is what? The address of the first element. So actually, starting next week or in 2 weeks, when we start using intensively pointers, dynamic arrays, we are actually doing this. But instead of writing this stuff like here, plus equals 3, we use the index brackets, which are like here. Remember? Some of you maybe did that in first semester, like here. So this is actually means jump 3 positions. Remember this? This is actually equivalent with this one. So pointer B of 3 is actually equivalent with pointer B plus 3. So generally we will use this syntax, but we will do this. And now I think you all remember that we do this in order to traverse an array. Okay. And pointer B will be the head of the array. So yeah, we will not subtract addresses and other stuff, but we will play with pointers. Okay, so we will move them through the space, through memory. Okay, so this is the power of pointers. So remember, pointers are variable which can help us point some addresses here. Great. Let's take a short break just to digest this stuff. And after the break, we will see how we can use pointers to send values in and out of functions. And I will show you that there is no other way. There are cases when we need to use pointers because otherwise we can't implement the solution. Okay, we can't communicate between functions. So this will be after the break. Yeah, I didn't. Sorry. Yeah, I forgot. Okay, but still, does this help to actually see the relation between pointers to pointers to pointers?
Yes, it was very helpful.
Okay, still I will save the image. Okay, this is something I will save them in the course folder, and you will get them on Git. Pointer to pointer. Let's say this is the name of it. Okay. So, any other question? If someone is still having doubts about this.
I have a question about the syntax.
Yeah, just speak a little bit louder. I can barely hear you.
It's better now.
Okay, I'm listening.
Do we need to have the parentheses, or we can just put?
Here the parentheses here.
No, it was on the source code in Visual Studio.
Where? Here?
Yes. Do we need those?
No. This is the way I learned them, because you see, it's helping me see what's the meaning of each asterisk and something. But generally, you will define them like here. But this is the moment when some of you will not know how many asterisks should be here. But if you take it logically and you just define the pointer and you say, hey, this is the pointer. So you start with this asterisk. And after that, you ask the second question, what's here? What's the type of this variable for which I want to manage it address? And you just go and check pointer A and you see it's an int asterisk. So it's another pointer to integer. Then this for me made sense. Okay, because a pointer is actually like this. It's a name with an asterisk, and here it's the type of this value. So in this way, I know how many asterisks should I write. Okay, because I will take it by this logic. Because otherwise it is just like 2, 3, 4, how many? Okay, so the parentheses are not mandatory, but like I said, in my mind, it's much more clear to follow them in this way, but they are not mandatory. So let's write both, or like this or like this. It's the same. Okay. We will play with pointers, and if you still have questions, please ask me. So why do we need pointers? Let's see why we actually need them. Because we will generally process data. Okay, so this is the purpose of our programs, to process data. So let's start with a fresh example here, like VB1 equals VB1, or let's say VBX equals 10, VBY equals 20. And what I want to do, because generally we will process data, is to try to interchange them. So I will try to do the standard algorithm. Okay, and I think you all know this, or you will remember it. So in order to interchange them, before that, let's print them. So end line, I will say X equals with VBX, just to see that, and Y equals VBY. Okay, so VBY. Okay. If I run this program, build, rebuild, I will see that VBX X is 10, Y it's 20. Okay, start without debugging. Okay, I have a compiler error. Let's see, where is that? Ah, yeah, I have redefinition here. Okay, so let's say same. And here, let's say pointer to another pointer. Okay, so let's rebuild again. Okay, now it's working. So debug start without debugging. And if I show you the screen, you will see that X is 10, Y is 20. Okay, so no surprise here. So what I want to do is to interchange them. And like I said, starting next week, main will be like a pseudo story. We will not write stuff that process data in main. Main will just call other functions. So we'll start coding in a much more cleaner way. So let's interchange them. And for that, I know I have this classic algorithm, VBX, okay, and after that, VBX equals VBY, okay, and after that, VBY equals temp. So now if I print them, okay, and run this again, build, rebuild, I will see that they are interchanged, okay, so start without debugging. And if I share the screen with you, you will see that now they are interchanged, 2010. Great. So what I want to do now is to make a function out of it, okay? Because writing everything in main is not the way we should do it. So I will define a function which will interchange two numbers. So let's define it here. So void, let's call it interchange, okay? And this interchange will receive two values, X and Y. Okay, I can name them in the same way, but I think it's clear that there are different variables. Okay, so there are no the same. I can call them VBX and VBY. Let's call them just to show you that they are not the same. Okay, so I know the algorithm. I just did it here. So I will just copy this from here. So let's see if that now I can interchange back the values by calling interchange, right? So now X is 20, Y is 10. I want to interchange them back to their initial values. So I have this function here. So I will go here and I will say interchange of VBX and VBY. And after that, I will print them because I want to see that now they are back to 10, 20. So this is my objective. I change them here and now I want to get them back. So build, rebuild. Okay, everything works okay. Debug start without debugging. And surprise, they are not changed. They are still 20 and 10. Okay, so as previous. But I know the algorithm worked because I just tested it. So why is not working? Why calling the interchange here is not changing back X and Y to 10 and 20? So let's see why. So I will clear this canvas. So now let's focus on X and Y. So this is the main stack. Okay, just forget everything else. So this is the main stack. And on the main stack, we have what? We have two variables, which are called X, VBX, and this is Y. And at some point, we had a temp. Okay, now initially, this was 10, 20. We interchanged them, and now they are like this, 20, 10. So in order to interchange them back, here, we are calling another function interchange. So what's happening when you call another function? This function is suspended. It's freezed. Nothing is lost. It's just freezed. And now you have another function which is executed, which is this interchange. And we know that when a function executes, it has its own sandbox, which is its own stack. And on that stack, you have the variables here and the ones defined inside it. So main is suspended. And now we are executing interchange, which has its own stack, its own sandbox. Now, what variables are on the interchange stack? Again, we have a VBX, we have a VBY, always check the list of input arguments, and we have a temp. So even if the variables have the same name, are the same, so is this X the same as this one here?
Oh.
No. So even if your functions have the same name for variables, They are not the same. There are different variables, okay? So they have no relation, only by name, but for the computer that doesn't help. So we know that when we call a function like here, we are actually sending the values of the variables from main to interchange. So here, always imagine an equals. This is like you check the interchange function VBX, and when you call it, this is like the VBX for interchange takes the value of VBX from here, and this is passing values, passing variables by values. So right before or when we call interchange, this is something like the blue X. So you just follow the order of parameters in the function signature equals the black X. Okay, so this is happening when we call it. And the same, the blue Y, because it's the second parameter, takes the value of the black Y. And I know this because I check the signature. So the first argument is X, the second is Y. And now I see that here X receives VBX and Y receives VBY. Obviously, if I write here by mistake Y and here X, I will pass to the interchange X my Y from here and vice versa, okay? Because this is what I decide. So right now, I receive the values from main stack and I receive them here. So X receives the value 20, Y receives the value 10. And now the function starts executing, which is the same algorithm. Temp equals VBX, okay? So temp equals VBX, which means this temp from here, the blue temp, equals VBX from here, which means here I get 20. VBY equals, one second, VBX equals VBY, and I'm playing with the blue ones. So VBX equals VBY, so here I get 10, okay? And the last one is that VBY, which is Y here equals temp. So now here I have 20. So you see, the interchange worked. It switched back X and Y, and it did the job. So the algorithm is okay. Now, what's happening here? When the function terminates, we go back to main. What's happening with the function stack? It's destroyed, it's clear. In reality, it's just left there in memory. Another function will overwrite it. But for us, this does not exist when we go back to main. And when we go back to main, we print X and Y, which is VBX and VBY from main stack, which have these values 20 and 10. So the algorithm worked. It interchanged the blue variables, but the main stack is still has the previous values, 20 and 10. And that's why we don't see the change back. So where is the mistake? There is no mistake. The algorithm is okay. The function works properly. The problem is that normally this function interchange will never be able to use these variables because you see always receive their values. Yeah, but wait a minute. Can we make a function see variables from here? Can we make interchange see these black boxes? And I think we know, because we have a tool which is called the pointer, which manages addresses. So instead of sending the values of the black boxes, 20 and 10, we need to send what? Their addresses. So if we want to make a function to play with other function variables, to access other function variables, we need to make it ask for addresses, not values. So if you want to change something outside your function, always ask addresses. So let's call this one interchange 2. So here I will say, hey, I don't want the value of the variable. Give me its address, p pointer x, and also give me the address of the other variable that you want to change from here. Okay. So now, this is how easy it is to do mistake with pointers if we don't understand them. So now I will say int temp equals px. Yeah, but I don't want to store in temp the value of the address. I want the value at that address, okay? Because I want to get 10 or 20. So I will say in temp equals px, asterisk px. And now you see how easy it is to do a mistake. If you write px equals py, this works. The compiler says nothing. Okay, and now I will say at the address given by py, copy there, at that address, copy the value from temp. So I changed interchange, so it will ask for addresses because I want the addresses of the black boxes. The values are useless because I can interchange the values here, but that will not help me change the black boxes. So I need their addresses. So I have written interchange to, and here I'm trying to replicate the algorithm. Okay, so let's say this is me trying to put asterisks by chance. Okay, and now let's see what will happen. So I will go back here to and call interchange to. Obviously, interchange to, you see, requires addresses, not values. So I need to pass the address of VBX and I need to pass the address of VBY. And let's see what's happening now. So now I want to print VBX and VBY. So build, rebuild, start without debugging. And let's see. It almost worked. It's 2020. Initially it was 2010. I was hoping to get 1020, but I got 2020. So it's a 50-50, okay? But it's not entirely correct. So, sorry, I just stopped the screen. So why didn't work the second time? So let's draw the image of interchange 2. This will be interchange 2 stack. And remember now, on the interchange 2 stack, I have a pointer. So this is the pointer to X. And I have another pointer, the pointer to Y. And after that, I have a classic temp. Okay, this is temp. And when I have called the function, again, just imagine that some equals are happening. Px equals y, py equals what? And now you just go to the call. So always check the signature, what you expect to receive, px and py. And now just check what you pass here. So you see px takes address of VBX. So this is actually takes address of X, and this takes the address of Y. So right now, we don't get here 20 and 10. If these variables have addresses, and they all have addresses, let's say this is AA, and the address here is BB. Now, these are the values that we get here based on this PX equals address of X. So here I get AA, and here I get BB. So that's why we are saying, hey, this pointer is pointing here, and this pointer is pointing here based on these addresses. Okay, so this one is pointing here, and now this one is pointing, sorry, my table is not big enough. Okay, here. Okay, now I have these values here. Let's follow the algorithm. Let's see why it works only by half. When I write temp equals the value from memory, this means asterisk, the value from memory at the address given by px. What means the value of px? The value of px is AA. So what's the value at this address? The value of AA is 20. So the first instruction, temp equals asterisk px, means I just copy here 20, but you see from where this 20 comes, it comes from here. This is the main stack. It's not our stack. So this function now actually plays with the main stack variables because it received their addresses. This is the effect of the first instruction. Now, the second instruction, px equals py, actually means this. Always remember, pointers are variables. So what means px equals py? It means this. Instead of having pound AA here, now we have BB, because they are two normal variables. So we just copy this value here. Yeah, but wait a minute. I think this is not something we wanted to do, to change the addresses here. No, I think we just wanted to do to copy over this 20, this 10 from here. Okay, so how do I copy this value from here when I have their addresses? Actually, here I wanted to say the value at the address indicated by px, which is AA. So the value in memory at AA takes the value of the address given by py. Okay, and right now, by just adding those two asterisks, I will copy this 10 from here over this 20 here. And the last instruction, py equals temp, but again with an asterisk, which means the value from memory given by py. So py has bb. What's the value there? This is it, equals the value from temp. So the last instruction will actually copy this 20 from here. Okay, so we take a value from our own stack and we copy it over here. And you see, now the function terminates like any other function. So we reach this point. What will happen with this function stack? As with any other function, we lose it. It's destroyed. We can't come back here. So this is lost. And when we come back to main, we print x and y. But what's the value of x now? 10. What's the value of y? It's 20. So this function has been terminated, but he had effects here on the main stack. And now we are back in main. So right now, if I'm running the same program again, okay, you see I didn't change anything here. So build, rebuild. Okay, Control F5 or debug start without debugging. And here it is. Now, sorry, works. Okay, x is 10 and y it's 20 back. Okay, so this is why we need pointers, because there will be many cases when we will do stuff here in a function and we want to save the results here or here or here in another location. And the only way to do this is only by pointers. So that's why we need to know how to play with addresses, because in order to do complex stuff, we need to be able to get out of the sandbox. So this is like in Park, if you want to build a sand castle, you need the tools from all the kids, and you need to be able to get out of your sandbox and get their tools also. Okay. So this is the power of pointers. This is what will actually allow us to do, to actually change values somewhere else. And this is what we will do all the entire semester. Okay, if you have any questions.